exchanger is basically a device that can transfer heat from one side to another. This heat exchanger is the two moving fluid streams exchange heat without mixing. The application of heat exchanger is one, refrigeration. This is where you can see your mom store your food and the ingredient for her to cook. Number two is a air conditioning system. This is where you can see around you the system that can cool down the entire surrounding, like classroom or in the library perhaps. And the other parts is like power plants, automobile radiator, this is you can see in cars, and chemical plant, and also petrochemical plants. So next we are going to look at the flow arrangement. So there are three types: parallel flow, counter flow, and cross flow. So first, parallel flow. Parallel flow is a two fluid that enters the exchanger at the same end and travel parallel to one and not to the other side. So as you can see here, this is the first inlet and the first outlet. And next is the second inlet and the second outlet. Basically, this is a cross, one from travel from the left to the right, and the other one is from the right to the left. Next, we are going to see the counterflow. Counterflow is fluid that enters the exchanger from opposite ends. So as you can see, this is the first inlet and the first outlet. And this is the second inlet and this is the second outlet. As you can see, the first is basically the same, but the second fluid enters is different. It's travel from below and going to the top. Also, counterflow is the most efficient as it can transfer the most of heat from the medium transfer. The medium transfer is where the heat generates, like the engine car or the compressor of the air conditioner. So next we are going to see the cross flow. Also is fluid travel roughly perpendicular to one another to the exchanger. So as you can see, both inlet is basically one side on another. So they travel from the same below and go to top. That's for both outlet, as you can see there.
Assalamualaikum. Today I will talk about type of heat exchanger. There are 7 heat exchanger in total. First is double pipe exchanger. Second is shell and tube exchanger. Third is plate and frame exchanger. Next is spiral heat exchanger. After that is air cool heat exchanger. Sixth is agitated vessel, and lastly is fire heaters. Next I will explain about 3 heat exchanger, which is double pipe exchanger, shell and tube exchanger, and plate and frame exchanger. Okay, firstly we will go to double pipe heat exchanger. A double pipe heat exchanger, also sometimes referred to as a pipe in a pipe exchanger, is a type of heat exchanger comprising a tube-in-tube structure. They are one of the simple and the cheapest type of heat exchanger. They can be used for high temperature, high pressure, and high viscous service. The second one is shell and tube heat exchanger. Shell and tube heat exchanger is a class of heat exchanger design. It is the most common type of heat exchanger in oil refineries and other large chemical processes, and it is suited for high pressure application. As its name implies, this type of heat exchanger consists of a shell with a bundle of tube inside it. The third one is a plate heat exchanger. A plate heat exchanger is a type of heat exchanger that uses metal plate to transfer heat between two fluids. This has a major advantage over a conventional heat exchanger in that the fluids are exposed to a much larger surface area, because the fluid are spread out over the plate. Next, we will go to the related formula for heat exchanger. For mass balance, we can say that m.1 equal to m.2 equal to m dot water. Then m.3 equal to m.4 equal to m dot refrigerants. For energy balance, the formula uses is E dot in equal to E dot out. Then we can substitute in two formula, which is m.1 H1 plus m.3 H3 equal to m.2 H2 plus m.4 H4.
So today we would like to present about the question which is related to heat exchanger. So question 1 which is from Chanel books. So example 5-10, cooling of refrigerant 134A by water. So here is the question. Refrigerant 134A is cooled by the water in condenser. The refrigerant enters the condenser with a mass flow rate of 6 kg per minute at 1 megapascal and 70 degrees Celsius and leave at 35 degrees Celsius. The cooling water enters at 300 kilopascal and 15 degrees Celsius and leave at 25 degrees Celsius. Neglect any pressure drops, so determine A, the mass flow rate of cooling water required, and B, the heat transfer rate from the refrigerant to water. So based on this diagram, we know that we have 4 points with which is 2 inlet, which is 1 and 3, and 2 outlet. So for inlet 1 and outlet 2, it is for water. And for inlet 3 and outlet 4, it is for refrigerant. So next, we proceed to the solution. So because of the question said neglect any pressure drops, therefore, the potential and kinetic energy is equal to 0. So under the state assumptions and observation, the mass and energy balance for this system can be said as like this, like the mass balance is m dot in equal to m dot out, which is if we make a difference between water and refrigerant, so we know that m dot 1 is equal to m dot 2 is equal to m dot water, while for m dot 3 is equal to m dot 4 is equal to m dot refrigerant. So for energy balance, the formula used is E dot in is equal to E dot out. Therefore, when we substitute into this formula, so it's become m dot 1 H1 is equal to m dot 3 H3 is equal to out m dot 2 H2 plus m dot 4 H4. So combining the mass and the energy balance, so we have to rearrange it to make it easier. So we combine water with water and refrigerant with refrigerant. So m dot water is equal to H1 here minus by H2, while m dot for refrigerant is equal to H4 minus by H3. So based on this equation, we know that for this, we are looking for this m dot, and H1 and H2 we don't know. M dot here is we know based on the question, and H4 minus H3 we still don't know. But we know that for H1 minus H2 is equal to H in saturated water. So to find H, the value of H1 and H2, we have to refer to table A4 in table properties to find the value of H1 and H2. For H1, it is equal to H fluid at 15 degrees Celsius. So based on this table properties, so we go to A4 table and find the temperature of 15, and we see at the HF, so the value is 62.982 kilojoule per kg. So it's the same, right? So next for H2, H2 is also equivalent to HF at 25 degrees Celsius. Back to the table of properties. Find 25 degrees Celsius and see the HF is 104.83. So that's the answer. Next, we have to find the value of H4 minus H3. But we know H4 and H3 is a refrigerant. So we have to see to other table. So for H3, we know that H3, the pressure is 1 megapascal and the temperature given at the diagram is 70 degrees Celsius. So we have to open table for refrigerant A13 and A11. So for the first one, which is 1 megapascal and 70 degrees Celsius. So we see here at table A13, it is a superheated refrigerant. So the pressure is 1 megapascal and the temperature is 70. So we have to find the value of H is equal 303.85. So here's the answer. For next, for H4, H4 is equal to 1 megapascal pressure, but the temperature is different, which is 35 degrees Celsius. So based on this 1 megapascal, but there's no 35 degrees Celsius, that means that is not a superheated region. Okay, next, for H4, the data given is the temperature is 35, but based on this saturated refrigerant table A11, there's no 35 temperature, 35 degrees Celsius here. Therefore, we need to do some interpolation to get the value of X, which I give it, the name is X. So based on this table, so we take 34 and we put 35, which is the value we want, and take the value for 36 because 35 is placed between 34 and 36. So for AHF, we take 99.4, and for 35 we state just X, and for 36 degree is 102.33. So to do the interpolation, we have to do like this: 35 minus 34 over 36 minus 35 is equal to what we have done, like the same to this side. So X minus 99.4 over 102.33 minus 99.4. So when we have to do some maths calculation here, therefore we got X equal to 100.865. So next, after we got all the information, we got the H1, H2 from the table of water, and H3 and H4 from the refrigerant table. So we have to substitute into this formula, which is M dot W is equal to H1 minus H2 is equal to M dot refrigerant H4 minus H3. So because of there's only one unknown here, M dot W, water. So when we do some calculations, and then we got M dot water is equal to 29.1 kg per minute. So that is the answer for question A. Next, for question B, to determine the heat transfer from refrigerant to water, we have to choose the control volume boundary that lies on the path of the heat transfer. Therefore, we choose the volume occupied by either fluid as our control volume. So the value of H3 and H4 we can find like I said earlier, which is in A13 and A11 table. So the formula to find B is E dot in is equal to E dot out. So QW in plus M dot H1 is equal to M water H2. So we have to rearrange and substitute, rearrange the formula because we want to get the QW in, which is the heat. So the formula become to Q dot W in is equal to M dot WH2 minus M dot WH1. So this is the formula, and then we substitute the value of M dot W from the earlier question and the H1 and H2 from the earlier question also. So therefore we got the answer is 1218 kilojoule per minute as the answer for B.
So question number 2. This question involves steam and water in a heat exchanger. So the question says that the steam is condensed by cooling water in the condenser of a power plant, and we are to determine the mass flow rate of the cooling water and the rate of condensation. So as we can see here, there are 5 assumptions. The first one is that steady operating conditions exist. The second one is that the heat exchanger is well insulated so that the heat loss to the surroundings can be ignored, and the heat transfer from the hot fluid is equal to the heat transfer to the cold fluid. Okay, the third one is that the changes in the kinetic and potential energies of fluid streams can be neglected, and fluid properties are constant. Number 4. Number 5, the last one is that there is no fouling, which means there is no accumulation of foreign particles or material on the surface, which might affect its performance. Now, looking at the diagram, you can see that the steam goes in the heat exchanger at 50 degrees Celsius, and water goes in the heat exchanger at 18 degrees Celsius. Moving on to the solution, there are 2 properties here that we can extract from the question. First one is that the heat of vaporization of water, HFG, at 50 degrees Celsius is given to be 2383 kilojoules per kg, and the specific heat of cold water at the average temperature of 22.5 degrees Celsius is given to be 4180 joules per kg degrees Celsius. We can also refer to it as CP. Next is the analysis. So first we can find the temperature differences between the steam and the cooling water at both ends of the condenser. So we're to find both delta T1 and delta T2. For delta T1, we need to minus TC out from the TH in. So 50 degrees minus 27 degrees will get 23 degrees Celsius. For delta T2, we need to minus TC in from the TH out. So 50 degrees Celsius minus 18 degrees Celsius, we got 32 degrees Celsius for delta T2. So next, we'll find the delta TLM, which is the logarithmic mean difference for the temperature. So the formula is delta T1 minus delta T2 divided by ln delta T1 divided by delta T2, which we have considered the values earlier. So plugging in the values, we'll get 27.3 degrees Celsius. So next, we can find the transfer rate in the condenser now that we have determined the value of TLM. So plugging in the values in the formula, Q dot equals to U times AS is the area times delta TLM, which we have determined earlier. So 2400 watts per meter squared degrees Celsius times 42 meters squared, which is the area, and times delta TLM 27.3 degrees, you get the final answer for Q dot is 2752 kilowatts. So next, we'll find the mass flow rate of the cooling water and the rate of condensation of the steam. So first, this is the formula that we'll consider here, which is Q dot equals to m dot Cp times T out minus T in of the cooling water. So we isolate m dot of the cooling water, so we'll get Q dot over Cp times T out minus T in. Plugging in the values from earlier, we'll get 73.1 kilograms per second. For Q dot, just plug in m dot and HFG of the steam. So isolate m dot of the steam. So plug in the values, Q dot over HFG, 2,752 kilojoules per second, divided by 2,383 kilojoules per kg, and we'll get the final answer of 1.15 kilograms per second.